According to the general theory of relativity, gravity is not a force. There are no gravitational fields. Gravity is kind of an illusion. Albert Einstein said the happiest thought of his life was imagining a man falling off the roof of a house. What made Einstein so happy about this wasn't Schadenfreude. It was the realization that this man, while he was falling, wouldn't feel his own weight. He would be weightless. And anything he dropped on his way down, well, it would remain stationary relative to him, or moving in uniform motion. The whole situation would be just like if you were in deep space, not near any large masses, with your spaceship at rest or coasting along at constant velocity.
Here, you would feel no weight. Objects would remain stationary relative to you, or if you give them a push,
they would move in a straight line at constant velocity. And you would be the very definition of an inertial observer. You're not accelerating, not in a gravitational field. All the laws of physics apply in your reference frame. Meaning there is no experiment you could do to distinguish your inertial reference frame from any other.
Now here comes the big leap. Einstein looks at these two scenarios and says they are equivalent, not just similar. Physically, they are exactly the same thing, which means man falling from roof is not in a gravitational field. There are no gravitational fields. And he is not accelerating. He is an inertial observer just like Rocket Man. Whoa, whoa, whoa. I mean, okay, I can see how both of these observers feel weightless, but man falling from roof is clearly in a gravitational field. I mean, he's right next to the Earth, and he's obviously accelerating. His speed is increasing by 9.8 meters per second every second, a fact that would become painfully apparent when he crashes into the ground. I know that these two situations look very different, but Einstein's equivalence principle tells us the one thing to focus on, the experience of the observer. If they feel weightless, then they are in an inertial frame of reference. Imagine if Rocket Man, coasting along at constant velocity and not paying attention, comes upon a planet a long way off in the distance. An external observer might notice that the path of the rocket bends ever so slightly towards the planet. But inside, Rocket Man would remain oblivious. He feels no force, experiences no acceleration. As the rocket gets closer to the planet, it goes faster and faster. But Rocket Man still feels weightless. For him, nothing has changed. So where on this journey would you say the frame of reference changes from inertial to non-inertial? An onboard accelerometer would never even register a blip. He has continued on his inertial path through space-time. So the logical conclusion is his frame of reference is inertial up until the instant he crashes into the planet. Okay, so how do you explain the curved path of his rocket without gravitational forces or gravitational fields? The answer is curved space-time. First, focus on Rocket Man's observation that the whole time he felt like he was
moving with constant velocity in a straight line.
He was moving in a straight line through space-time. But space-time around massive objects like planets is curved. So that's why his path appeared curved to a distant observer. Now this isn't as unusual as it seems. Airplanes, for example, always try to fly the shortest route between cities. Essentially, they just go in a straight line. But since the Earth's surface is curved, the shortest path doesn't look like a straight line. These shortest paths over curved surfaces are called geodesics, and we use that same word, geodesics, for the straight-line paths followed by inertial observers through curved spacetime. Here's another analogy. Imagine you and a friend are standing 1,000 kilometers apart on the equator. Now you both set off due north. Over time, you will come closer together, ultimately bumping into each other at the North Pole. It's as though there was a force pushing you together. But you didn't feel a force, and your friend didn't feel a force. Gravity is just like that force. It doesn't actually exist. The real reason for you coming together was that you were both on straight paths, geodesics, on a curved surface.
Astronauts on the space station are weightless. That means they too are inertial observers traveling on a geodesic. But the Earth curves space-time around it, which is why their straight-line path appears as a helix. It only looks like a circular orbit if you forget the time dimension. Don't forget, we are all moving through space and time. Space-time.
This is the standard bent sheet analogy for curved spacetime. But I think this demo is misleading. It allows you to fool yourself into thinking you understand general relativity when the intuition you're actually drawing on is just that objects like to fall towards the middle of a well due to the gravitational force. But in general relativity, there is no gravitational force. What you should be thinking about is objects traveling on a straight line path through spacetime. It just so happens that spacetime is curved around massive objects, so that straight line path doesn't look like a straight line. Matter tells spacetime how to curve, and spacetime tells matter how to move.
Now let's go back to deep space. What happens if you turn on the rocket thrusters and accelerate at 9.8 meters per second squared? Well, someone outside would see all objects remain stationary, while the floor of the rocket accelerates into them. Inside the rocket, everything would appear to accelerate down to the ground, and you would feel a force pushing up on your feet, the same force that's pushing up on you as you watch this video.
This situation feels exactly the same as being at rest on the surface of Earth. Because we are at rest on the surface of Earth.